This video will cover problem 4, focusing on significant figures and absolute versus relative error, using an 8-bit binary floating point computer as a case study. The core problem is to determine the absolute and relative errors when an 8-bit binary digit string represents the true value of 0.2 as 0.11001100 multiplied by 2 to the power of -2. This falls under significant figures and error propagation in floating point computation. Key concepts include absolute error, which is the magnitude of the difference between the true value and the stored value. Relative error is the ratio of absolute error to the true value. Significant figures are the number of digits considered correct, starting from the leftmost non-zero digit. Step 1 is to convert the stored binary value, 0.11001100 times 2 to the power of -2 to its decimal equivalent. Expanding the binary value and multiplying it by 1/4 yields a stored decimal value x, which is 51 over 256, approximately 0.199217875. Step 2 is calculating the absolute error using the formula. Absolute error equals the absolute value of the true value minus the stored value. Using the fractional forms of 1/5 for the true value and 51/256 for the stored value, the absolute error is found to be 1/1280th, or approximately 0.00078. Step 3 calculates the relative error using the formula. Absolute error divided by the true value. Dividing 1/1280th by 1/5 results in a relative error of 1/256th, which is approximately 0.0039 or 0.4%. In summary, the stored binary value 0.11001100 multiplied by 2 to the power of -2 equals 51/256, or about 0.19922. The absolute error is 1/1280th, or roughly 0.00078, and the relative error is 1/256th, or approximately 0.4%. As a bonus, let's briefly review significant figures. The count starts from the first non-zero digit. For example, 10.62, 0.05715, and 4.600 all have 4 significant figures. Scientific notation helps resolve ambiguity in numbers like 4,300.